So as you can see here, our first talk is by Luke Anselin on spatial analysis and CyberGIS, but I'd like to just give a couple of moments introduction for Luke. Luke is chair of the School of Geographical Sciences and Urban Planning at ASU. He's one of those rare individuals who can combine significant theoretical contributions to a discipline with significant practical contributions. And I find this quite inspiring. So some phenomenal work on spatial econometrics, coupled with what he's going to talk to us about today, is more practical work on how the tools and methods from that research can be made available to a broader community. Thanks, Luke.
Thank you, Mark. Yes, I changed my title a little bit. Shawan changed it on me in the program, so then I figured I'd pull the same stunt on him and change it again. Really what I want to do today is give you an overview, as the session is called Progress and Tools, give you an overview of what we're trying to accomplish at the Geoda Center as part of this project. And the goal is, of course, to bring spatial analytical functionality to a CyberGIS environment. As everybody knows, this was funded, and I'm just representing a much larger team. Several members of the team are here. Some of them are rotating out and others are rotating in. So this is constantly in flux, but it's much more than just the people on the title of the slide. So the goal is to develop cyber infrastructure in support of spatial analysis. And in one of Mike's several pieces of writing on this topic, this was succinctly put at the end. And that's really what we're trying to do. So what does it mean specifically? And I'm quoting here from the proposal, and so it's a bit of proposal speak that you will recognize, but the emphasis is on composable and interoperable pieces of software. And this is oftentimes very different from the way we develop software. And in our team, we've spent many, many years working on desktop spatial analysis software, which typically is not interoperable and typically is really focused on developing particular functionality, but doesn't necessarily think about how all the pieces fit together and how you can have the pieces work separately in a modular fashion, which is very much needed here. The second one of the several project goals that I would like to focus on is that we exploit the spatial characteristics. So this is very much in line with what is special about spatial. This is not just regular analysis, but we deal with the problems of including location, relative positioning, distance, contiguity, things like spatial weights matrices, which don't really appear in many other fields. And so how do we exploit these and also tackle these in terms of moving analytical operations to the CyberGIS environment? The challenge, as was mentioned a couple of times in the earlier talks this morning, first of all, most, if I don't want to say all, but most current spatial analysis or spatial econometric software was written for a single CPU. So just the thought of using algorithms that are scalable in the sense of the previous talk never was considered. So the challenge of moving to a CyberGIS environment is that we really have to rethink many of our algorithms and processing approaches and also rewrite the algorithm, rewrite code so that we take advantage of the cyber infrastructure. It's not just moving a desktop to a supercomputer, it's really taking advantage of the scalability that high-performance computing allows us to do. And a third very important challenge that we, I think in our field have tackled in terms of the data are concerned to a considerable extent, but not in terms of the functionality. That's the lack of interoperability. Functionality for analysis, I mean. So the idea we have, the specific thing we're trying to work towards is something that I have called a spatial econometrics workbench, along the lines of several workbenches that NCSA has developed over the years. It's really a framework in support of spatial econometric research. And what we mean by a framework is not just functionality, but the flexibility to put this functionality together in new and innovative ways, in other words, in ways that we haven't necessarily thought about. So we try to develop something that is a toolkit for running large-scale simulations, estimation, model comparison, and so on. And specifically, we need to develop support for the idea of a scientific workflow in this context. And what I will be speaking about specifically today is how we leverage another project that we have, which is not Geoda, but PySAL, which is a library, an open source library for spatial analysis. So how do we leverage PySAL to move it to a CyberGIS environment? Just to give you a few words of background about PySAL, it's an open source library of Python routines for spatial analysis, and it's a growing library. It includes some basic geocomputation, and then a lot of things that are really pulled out of our experience of 15, 20 years of developing various pieces of spatial analysis software, things like spatial weights, spatial autocorrelation statistics, spatial econometric regression methods, estimation methods. There's a website, the code is open source, it's available, anybody can look at it. It's hosted on Google Code. This gives you an idea of what the website looks like. I'm very proud and happy to mention that we have stuck to a 6-month release cycle, and PySAL 1.4 was released exactly on July 31st. So we are on time. There is documentation, both in the form of tutorials as well as extensive documentation generated by the code about the API. This is the multi-headed monster. This is our vision of PySAL. It's also now become the logo, kind of by default. As you see, a focus on specialized functionality, computational geometry, weights, spatial econometrics, space-time dynamics, exploratory analysis, clustering, and each of these have growing multiple heads, and it keeps going. It's very modular. So what we have done is thought about the functionality that we had developed in various other pieces of software and kind of take it apart as a library of atomic, or as much as possible, atomic functions that you can then put together any which way you want. The high priority items that we're currently working on for moving to a CyberGIS environment are spatial weights, because they are so fundamental to many operations. The application of global and local spatial autocorrelation, where the inference is carried out by means of permutation, which is simulation-based and highly scalable, and then various types of simulation estimators that come out of spatial econometrics. Now, how do we do this? And we see 3 main priorities in this process. First of all, we have to move away from the desktop, and we have to turn all this functionality in the library into an accessible form through the internet to become a part of a cyber infrastructure. So we have to turn them into web services. Secondly, we have to think about scalability and performance. So we need to rethink some of our algorithms and look at parallelization. This is not as simple as it sounds. It's not a one-shot solution. And I think we're spending a lot more time thinking about our algorithms rather than necessarily implementing this in a parallel way right away. And then the third point, which is something that in my original plan for my talk I wanted to spend more time on, is interoperability, the need for metadata and provenance tracking, which has been highlighted in a couple of papers by Xiaowen and his group for spatial analysis, but it is something that is still mostly lacking. There's a lot of progress in terms of data interpretability and basic GIS processing, but when you move into the analysis, there's not a lot there. So let me talk about each of these in turn, and then I'll close with some comments about a roadmap of where we are going with this. So the PySAL web services, basically, this is a lot of work creating middleware and wrapping code around the core PySAL code. So we don't actually have to touch that functionality, but we have to put all the infrastructure around it, and we have to make it available. And specifically, we have made it available. It's still a prototype, but it is available through the NCSA CyberGIS portal, and the code itself is now running on the ASU Decision Theater cluster. And the prototype that we have running has to do with spatial weights. So basically, we have this setup where we have a client tier, which is right now primarily a web application. So there is a user interface that you access through your browser, but just as well, and I'll illustrate this a little bit, you can access it from the command line. And of course, the goal is that eventually pieces of software will be able to discover this functionality and then automatically integrate it with whatever they are doing. So you have the typical layers, and at the very back end is the decision theater cluster, and then PySAL sits on there, and then all this other stuff takes care of the interaction between the client and the actual server. And there's an additional cycle in here, which is part of the challenges, and I'm sure some people will talk about this later. Part of the challenges in the cyber infrastructure is authentication, making sure that the resources are used by the people who are supposed to be using them. And so there is right now an NCSA UIUC token service which keeps track, is kind of the gatekeeper. Once you're in, then you have access to all the resources, but to be in, there is a certain protocol that we have implemented. This is an example of what this looks like through a browser. There is a web interface, and it looks almost like the desktop application. It's not quite as fast, and there are issues with moving data through the pipeline and all that kind of stuff that we all know happens to you when you move to web services, but it looks like an application. And in addition, you can also access it from a command line level. Now, this is kind of clunky, but it does give you all the power of accessing all the options and flags and other opportunities built into the functionality of PySAL. So these examples at the bottom access specific functions that are part of the library, pass a bunch of parameters, and then this all gets kind of packaged and with interfaces with the token service to make sure that it's authenticated and then sent to the server. The server processes it and posts back the results. So this is where we are right now with the web services. This is in a prototype stage. It does work, but it's not production grade by any means. And so the idea is, as part of our progress strategy, is that we are starting and experimenting with something that we know very well and understand very well, and identify the challenges so that we can then scale it up and move much more functionality into the system and make it available through the CyberGIS portal as part of the infrastructure. The second challenge, as I mentioned, was parallelization, and I think Rob talked a little bit about this yesterday. So why do we need the parallelization? We really need to scale up. And in some of our types of problems that we encounter, the problem is not so much the complexity of the model or the size of the data. I remember when I was still here at Illinois and was in meetings with NCSA, that the kind of data sets that we were thinking about were really toy problems when it comes to astrophysics and molecular dynamics, and this is totally different world. So how do you motivate the need for this high-performance computing then? Well, one major motivation is that it's all fine for an astrophysics simulation to run for a week and then finally have the solution. If you're in a decision support environment, you can't wait for a week. You can't wait for a week to get tomorrow's weather. So these are the kinds of situations where we need fast turnaround, even though we may not have the petabytes of data sets that need to be manipulated. We do need to run these models, and rule of thumb is 7-8 seconds turnaround in real decision environments. And for many of the models, you simply cannot get that kind of performance unless you go to HPC. You can't get it on the desktop. And so what we've been experimenting with is some methods in spatial econometrics in particular where we do run into bottlenecks on the desktop, meaning that we can run these models, but it takes a week for a problem with 6,000 observations. And this is all fine if this is your dissertation, but it's not fine if you need the answer right away. So that's what we're focusing on right now. And so we, because we had all this investment already, a lot of legacy code in PySAL, we have focused on the use of Python. Now, Python might not be the best for ultimate performance in a high-performance computing environment, but it's incredibly fast for development. So it allows us to learn a lot very quickly and also to identify those particular problems where Python falls short and we have to move to C++. And so as part of our research, we've been looking at different Python libraries for parallelization, and initially focused on multi-core and GPU environments, not so much on clusters yet, which is ongoing. And very quickly we discovered, and this has also been mentioned this morning, not everything can scale very well. In fact, several spatial analytical problems don't scale well at all as is. You really have to rethink them and rethink the way you do them. And so some of the initial results that we do that Rob reported on yesterday is that there are some things you can do very, very well, and they scale very, very well. Anything having to do with permutation inference scales very well. Anything having to do with local analysis, so local indicators of spatial autocorrelation, scales very well. Anything having to do with simulation estimators, where essentially you run the same thing many, many, many times, scales very well. But what doesn't scale so well are many of the other problems where you have a mix of parts in the processing that are sequential and simply cannot be parallelized, and then other parts that can be parallelized. And the experimentation that we carried out in our team showed that we run into many counterintuitive results. We have not been able to find anything that is immediately generalizable. So it's very much a case-by-case, almost hand tuning, which is not a very scalable way of approaching this. But it gave us some expertise that we can now scale up to some of the other problems. So we have done quite a bit of work on the local Moran, parallelizing that. Rob reported on map classification yesterday. We're working on regionalization, contiguity constraint clustering methods, and some of the simulation estimators that I mentioned. And this is part of the types of surprises that you run into, where we compare 3 different types of technologies for parallelization, and you see that you have a very fast improvement in performance up to a certain size data set, and then it flattens out or might even get worse, depending on the types of software tools that you use. And so this was, not all parallel libraries are created equal type of lesson, and we are still working towards learning more about this. Then the third item that I wanted to touch on today is something that I've started to pay more and more attention to, and is the whole idea of an idea of a scientific workflow. And as Mike put it, how do you answer questions? And not the focus on the specific steps. So here I have a local Moran tool, go use it, but more turning it around and where are these hotspots? Where are these cold spots? And then how do I figure out how to get there? What do I put together? Which data sets? Which tools? How do they sequence each other? And then, of course, once you start sequencing tools, you have to know where they come from and what particular sequence you used. I mean, all too often, when we get carried away in our analysis, we try this, we try that, and then all of a sudden it works, and we forgot how we got there, right? And this is the key notion of provenance. And some statistical software has this history feature, and Unix has history feature, where you kind of can repeat your command, and so basically that's a very early form of provenance tracking. But once you start combining different data sources, different manipulations, and different analytical operations, you basically can formally express this in a graph structure, and this is a standard way of operating. And this then ideally would enable replication, which is another key concept. Now, it's not as easy as it sounds. In spatial analysis, we combine data with processing. So we really have two types of metadata, if you wish, or two types of provenance. One has to do with the data. Where do they come from? What projection? Who created them? Who simplified them? All these kinds of things. And then another one has to do with the processing, not just which processing was applied, but in what sequence, what assumptions were used when there is a choice of different assumptions, and so on. So the combination, the first part of this, the attribute data is fairly well understood, and there are solutions for this. The second part, much less so. And just to give you an example of spatial weights are a way to formalize a neighbor structure in a spatial data set. And they're a key component of any spatial autocorrelation statistic or spatial econometric operation. And you'd be surprised at how little is known about spatial weights. And I'll give you an example in a few minutes. So where do these weights come from? They typically are initially constructed from a spatial data source. Say if they're based on contiguity, you have some boundary file, and then you apply an operation to find out which polygons have common borders or common vertices, for example. Or if they come from coordinates, then you figure out the distance between these coordinates. But of course, you have to know whether these coordinates are on a real sphere or projected, because the distance measures are different. And current practice, you don't know this. And I just give you an example of one of the latest routines in PySAL, Spatial Econometrics module. This is a very fancy econometric estimation method, and this is the result. And the result says that the weights matrix that was used was this file, south underline K6 GWT. And the file used to carry out the kernel weight calculation was south underline EP underline K20 KWT. Now the system didn't come up with these names. The user came up with these names. So if the user had just called this south 1, south 2, there is no way you would know what this was. Now, because I did it, I know that the first one is a K nearest neighbors with 6 neighbors, and the second one is a kernel weight based on the Epinechnikov weights, and I used an adaptive kernel with 20 nearest neighbors. But if I didn't do this, there is no way any computer system can figure this out unless you build in metadata. And I was aware of this problem very early on, and in the GAL and GW2T file formats that are used by most spatial analytical software, they were initially proposed as part of SpaceStat in 1994 or 3, and then were adopted by pretty much everybody else who implemented spatial analysis in R, Geoda, PySAL, etc. And the idea was to have a header line in the weights file. The weights file is just a text file that contained some of the metadata. And the idea initially was to use the first code, which is just a 0, as some way of telling you what kind of method was used. We never got that far. Then the rest is just the size of the data set, a little bit of metadata, the shapefile that it was derived from, the name of it, and the key variable that is used to construct the weights. But that's it. Nothing tells you, is this distance-based, is this care nearest neighbors, is this a kernel weight, or anything like that. Now, there's been a profusion of different formats to store weights in the field. There are 6 or 7 in somewhat major use. The major ones are still GAL and GWT, but there are many other ones. And one of the things we have in PySAL and in our web services is a conversion utility, right? Something that moves one format to the other, which is very useful in applied work. But really what we need is metadata. And the way we like to think about this is to separate the data source from the operation. So the data source typically is either polygon or coordinate files, and there is a lot of work and established practice for metadata. We don't have to reinvent the wheel. That already exists. For operations, there really isn't much there. There is some work in OGC as part of WPS, but it's primarily focused on GIS data handling and processing, not so much on analysis and forget about spatial econometrics and those kinds of very esoteric things. So what we're thinking about is to separate out the metadata, and this is all very much work in progress, by separating the metadata about 2 basic tasks in the weight construction. One is to set up the actual network structure, basically the 0-1 structure or the graph of who's connected to who. And then the second one is what are the values of the weights? Are they like which kernel function did you use and all these kinds of other things? Do you use standardization, transformation? So we have a prototype of a content model. We have a taxonomy of weights and weights functions and weights operations, and this is all very descriptive so far. So we have the operations, we have the schema. What we don't have yet is what we really need is, this is all done by hand. So that doesn't really scale very well. So we need automatic generation of this. We're starting to think about structures to do this, and we need automatic retrieval of this information. So that's what our work is focusing on right now. So let me quickly go through the roadmap in my next 2 minutes. 3 major tasks: methodological refinements, obviously algorithm improvement. Specifically, we're focusing on something which may seem very esoteric to you, spatial probit or tobit, but it has to do with limited dependent variables, 0-1s, which is very common in applied empirical work in the social sciences, but it doesn't scale on the desktop. And this is where the high-performance computing is key. You can't do it without it. The same space-time local methods, such as a space-time scan statistic, doesn't scale well on a desktop, and you need to move to high-performance computing. In terms of making things operational, we keep working on our web services. We are really going to focus, and we've started doing some work on this automatic provenance generation, initially as part of PySAL. So PySAL will be generating metadata as you do stuff in PySAL, and then we'll figure out a way to store this so that it can be accessed. And then finally, and Mike mentioned this, and I think everybody will mention this, this is not if we build it, will they come type of project. We really have to make the case that this is useful, that there is an added value, that this allows you to do things that you couldn't do otherwise. And I think in the specific case of spatially correlated limited dependent variable models, that case has been made. And then the last 2 bullets, and I have them in every presentation that I make, is the importance of training and documentation cannot be underestimated. There's lots of great open source tools out there with very poor documentation, so nobody uses them. And to facilitate participation, the threshold has to be lowered. The user interfaces have to be intuitive. I can understand why CyberGIS Gateway has a token system, but it's a pain in the neck, and it's not something that you're going to get a mass of users buy into and access the functionality. So all these are things we need to address and need to think about. Thank you.
Thanks very much, Luc. Questions for Luc? We have time for one or two questions. Yeah. Wait for the microphone, please.
So you speak a lot about generation of provenance and metadata. What do you envision like on the other end of how this metadata is going to be consumed, and do you see any automation of how to include provenance and the metadata into the next steps of the analysis?
Well, it's actually a tricky problem. What we're looking at is initially the extent to which we can use existing tools first. So we need to, as we carry out operations, say in PySAL, store the information on the history of the process in a systematic fashion. So obviously that's going to be some kind of XML that then needs to be understood by the systems that maintain this. And that's what we're focusing on right now. We would rather not reinvent the wheel. We would rather use existing tools, provenance tools that are out there with database structures so that repositories that can be accessed by web services. That's the ideal. I don't know right now. I can give you the answer of how exactly we will do that, but that's how we're thinking about it.
Thank you.
Any more questions for Luc? Dawn.
Thank you, Mark. Thank you, Luc. I really enjoyed the presentation and the idea of some kind of a metadata standard for analysis. Do you, with the content that you already have, the taxonomy, the XML schema, do you foresee actually getting to that point where there is standardization for this metadata, particularly something that the OGC can facilitate?
I'm glad you mentioned OGC. As you may know, ASU is becoming a strategic partner of OGC, and this has been one of my main things over the past year to be involved with that. And the ASU, the Geodis Center main role in that effort is pushing forward the idea of metadata standards and provenance tracking for spatial analytical operations within a larger context of standards for model builders.
Thank you.
Okay, thanks very much, Luc. Quick, one more round of applause, I think.